So in this video, we're going to take a look at what it looks like to do a regression test on slope to determine if maybe there's a linear relationship between two variables. So a quick thought here. Uh, if we have a set of bivariate data, so that's something to create a scatter plot, and if we expected no relationship, what we might expect that scatter plot to look like is just a set of random observations kind of all over the place. So if these two things aren't related, then there's going to be no real discernible pattern in the scatter plot. And so a line of best fit, we could draw one, but it'd probably just do something like this, where all of a sudden, if there is no relationship, the slope of that line is going to be 0. So what we're going to start to take a look at is we'll be given some set of data, and the objective is to see, well, is there a relationship between those? In other words, does it look like there's a positive or negative slope to the line? So what we're going to do with it is we're going to use this thing to determine if a linear relationship exists, test for slope. And in other words, does the slope differ from 0? So what happens is we collect our data, and then we find that line of best fit. Right? And typically this is found, there's the linear regression function in the calculator. And keep in mind with the stat, we always use the ones a little bit further down that list of a plus bx. So what we're going to do with that, just like we've been doing with sampling techniques so far, is we're going to use that sample to try to estimate what the true values are. The hypothesis here, the null will always be that beta equals 0. In other words, that there is no linear relationship. Just like we saw with chi-squared for independence, your null was that there is no relationship. The null here is no linear relationship. Versus a possible alternative, the slope is not 0. In other words, there is a linear relationship. And I'm going to run out of room for relationships, so I'm just going to abbreviate. But we can actually go a step further with the alternative, and maybe we take a look, is there a positive linear relationship, in which case the slope would be positive. And maybe there's a negative, in which case there would be a negative relationship. One thing to note very quickly, we're always going to do a test on the slope. We will never use, there's never a slope or a test for y-intercept. We're never going to do a test on that. And the biggest reason there, if you think back about, a few months ago when we talked about regression, the y-intercept doesn't always have a legitimate interpretation. We can always interpret it as when x is 0, y equals, or then y is the slope intercept. But if you think back, a lot of times those didn't necessarily make sense. We could plug things into the right template, but they didn't necessarily work out for us, whereas slope always had some type of context in the problem. It always had some type of meaning. So the t-test for slope, here are our conditions. We want to make sure our data is linear. If we have a quadratic looking set of data, there's no point in running a test for slope. We can tell that that's not linear. So if it's roughly linear, let's move forward. Here's our randomness. And then these last two, the equal variances and errors are normally distributed. Really, what we would just want to make sure, if you remember back about this stuff too, residual plot, if a residual plot looks good, then that tells us, hey, linear is probably a good fit for this model. Let's move forward. Okay. So there's our test statistic. So B is going to come, this is our predicted, this is from our prediction equation, our line of best fit. All right. Our least squares regression line. It's got a few different names. This beta value right here, if you remember, we always work under the assumption that beta equals 0. So this is going to be 0. And then standard error of the slope. So this is standard error of the slope. And really what you're looking at there is they've already done all the dividing by square root of something, or they've already done all the work underneath. They're just going to kick back and number. So there's your standard error of the slope. If you have to run a confidence interval, again, there's that b value and the standard error slope. So b, again, same thing as before. It's the prediction. You get that from your prediction equation. There's standard error of slope, and then t star is going to come from your t-table. And it's based on, again, degrees of freedom. And so the one thing to realize here, degrees of freedom is going to be n-2 since it's bivariate data. So let's say that we want to run a test to determine if there is a relationship between two variables. So here's some data on blood alcohol levels versus number of drinks consumed. And so if you take a quick look at what we see here, there's the line of best fit sitting right there in that data output. So again, the A is negative, well, this thing's going to write for me. My y-intercept is negative 0.013, and my slope is 0.018. So in this particular case, that y-intercept is basically saying at 0 drinks, your blood alcohol level is negative, which has no real meaning in this context. As a quick reminder, the interpretation of that slope for each additional drink, so as x increases by 1, the blood alcohol level increases, excuse me, make sure I can spell, left the R off, by 0.018. That has a context, right? As someone would have more drinks, their blood alcohol level should rise. So if we take a look at the conditions, right, the data does look, it looks pretty linear. If this is a random sample, and then you take a look at the variances, and then this is a box plot for number 4. There's a box plot of the residuals, but even just looking at the residual plot right here, if we go back to that particular unit, that's a good looking residual plot. Good scatter, no real pattern, so everything's good moving forward. So if we'd like to run the test, so here's what the calculator, if you actually were to run the test, this is some of the stuff that would kick back to you. On the TI-83s and 84s, this line isn't here, so we'll take that out of the equation for us so we don't get confused. But now it's just a matter of plugging values in, right? So there was our slope from before, right? So there's our slope. Remember that beta equals 0 from the null hypothesis, and then there's your standard error right there. What's nice is they give you the actual t-value, so you just have to plug things into the formula in the right place, and you don't actually have to do the math. We actually already know the p-value. The p-value is given to us. It's very, very small. There's degrees of freedom, 14, right? We're running a t-test. Let's make sure that we mention that. There's the p-value, excuse me, at 0. So in this particular case, 0 is definitely less than 0.05. We would reject the null. So keep it in mind, the null was that beta equals 0, so we rejected that. So it looks like the alternative, right? Let's say the alternative, the slope is not 0. There appears to be a linear relationship. Notice I didn't give you a direction one way or the other, and that was simply because, remember, RHA was that beta is not 0, so that just tested for a linear relationship. You could also run a confidence interval on the slope. So again, there's your formula there. Let me move this box out of the way so we can see that clearly. So, and it's just a matter of plugging these numbers in. That T star, again, so that's from a 95% confidence interval and 14 degrees of freedom, easy to find. And, well, that's actually the wrong number there. This should be, there's a typo. 0.0204. So that would kick back to you. There's those numbers. It's just plug and chug, and so we're 95% confident the slope is between those two numbers. Now what's interesting, that entire interval is positive, right? Entire interval is positive. So that lets us in on a little bit more information than the test did above. So it appears we have a positive linear relationship exists. Now that's if we're actually given the data and we can run through the test very quickly, plugging the values in from the calculator. Sometimes they're just going to give you data. They're going to, here's some data that somebody ran the test. So here's data on a relationship between waist length and someone's weight. So 22 people were looked at. So it might be worth going ahead and noting. So the degrees of freedom will be 20. So let's say that we wanted to find the line of best fit. This is kind of review. So just as a quick reminder, how to find those two values. So the line of best fit for this then would be y hat equals a plus bx, and just pulling data from the computer output, excuse me, and plugging them in. So a question here might again ask you, interpret the slope, interpret the y-intercept. Right here, obviously, you know, that tells you that if someone's waist length is 0, then we'd expect them to weigh negative 36 kilograms. No context at all. But we would expect, as their waist length increases, we expect their weight to go up by 1.29 kilograms. Right? So quick reminder there. But let's say that we actually wanted to run one of these tests. Let's say we'd like to run a t-test for slope. Well, all the information for slope is coming from that bottom line right there. Our beta value is at 1.29. Standard error, it's given to you. If you take a look, if you were to plug that into the calculator, you'd realize that equals 10.15. Well, that value, again, it's given to you. And the probability that we get that test statistic, the probability, again, if we were to run, is there a linear relationship? Let's just beta does not equal 0. So that's a two-tailed test. That's why that probability statement is going, above 10.15 and below 10.15. So this area, right, so we're 10.15 standard deviations away from the mean, which is pretty far away, but for the sake of this problem, right, so that's a two-tailed test. And that probability is also given to you. So we can now draw a conclusion. We didn't actually have to go to the calculator. We didn't have to do any work for it. It was all given to us pretty quickly. And then also we can run an interval off of this. So let's say we wanted to run an interval to estimate what the true slope is. Right? So if we wanted to run a 95% confidence interval to estimate true slope, we can pull all that right from the data output. Again, beta, it's right there. There's your standard error. With 20 degrees of freedom, which we talked about earlier, that t star, if you go to the table or you do inverse t, remember, if you're doing inverse t, you have to use 0.025 because you got to split that in half, and then 20. And at that point, it's just a matter of plugging in and going with it.